going to look at some tangent line and the gradient function and its graphs and apply these concepts to polynomials and exponential trigonometric functions. So just welcome again to our session. Students always ask which CAS page should you use in a task. Well, a graphs page is designed to find values of points of interest of a function as decimal approximations. A calculator page or a notes page is designed to find values of points of interest of a function as exact values, or if we like, as decimal approximations. We're going to use all those pages tonight. Now, just a little bit of background information. I know we've all seen this picture before about the derivative, and we've got our point P that we're going to find the derivative. We've got a tangent line for that. We've got a point Q, and we're looking at this secant that's here. And we're going to be able to drag this point closer and see what happens. We'll have a look at that shortly. Now, the relevant equations that we have in this section would be to find the gradient of the secant line, which is another word for the average rate of change. And we know it's taking the 2 points on the graph that you just saw before and dividing by the distance apart. And then to work out the instantaneous rate of change, or the gradient of the tangent line, or the derivative equation, we're then going to take the limit as the distance from the 2 points decreases to 0. We've all seen those before. Now, at the moment, we've got a little bit of a busy graph here, but just to take you through that, just to remember what you did back in year 11 and hopefully again in year 12, we've got a blue point, which is where our tangent is. This is our green line, according to this tangent line here at 2. We've got our red point, which is our point on the curve up here. The red line is our secant line, and our aim using that limit formula is that when we take the point closer, we notice the gradient of the secant slope is approaching 2, which is the gradient of our tangent line. And it's just for our example that we've got there. We can also see up here the two equations that are involved, our quadratic and the linear line, which is a secant line, and we see that the gradient, as we get closer and decreasing the value of h, which is going 1 to 3 at the moment, we see that the gradient of that line, secant line, is approaching 2. And if we go closer again, it's now 3. And if we went closer again to 1, it would now be equal to the tangent line. So our limit formula does show how we do that. Okay. I'm just going to move across to a different screen just there. I'll just give me a moment just to catch up with the pages. Okay, this looks a little bit better. So we're going to consider the function f of x equals 2x squared minus 15x minus 8, and we're going to find the equation of the gradient function. Now, there's many ways we could actually do this, and it depends on what you want. Well, we can go through, and the first thing we could do is define our function fx. If we're going to use the function more than once, it's probably a good idea to define it. It's there. And so, menu, actions, oops, we didn't want that to happen yet. Let's just go back there. Menu, 1 and 1 define. And I'm going to call it f1x, and that'll become apparent to you quite shortly as we go through this. And it equals 2x squared minus 15x, and we've got minus 8. Okay. Now there's a couple of ways we could do this. We could go through and use the menu button there. Calculus is what we're looking at, and we could go derivative, and what that does is bring up the template. But a much better way of doing that is using the shortcut, which is shift and minus. And then our variable is x, and if I click inside the bracket and press var, it tells me the variables I've got at hand, which is f1. I put in the x, and all good. The derivative, or the gradient function, is for x minus 15. Now, we need to find the value. Part B, find the value of the gradient function when x equals 6. Again, there was a few ways we could do this, but I think the easiest way would be is to just go up arrow in the history, press enter. It pastes it into the current line of working. And then if we go control equals, and if I hit the back arrow, it takes me down to the given that bar. And then if I just put in x equals 6 and press enter, so the gradient at the value when x equals 6 is 9. So now another way that we could actually do that, let's say that before we got up to this question that we actually were graphing these things. And if I press Control G to bring me up to the graph entry line, you notice it went to F2x. Well, if I go up arrow, because I called it F1x, my original function, it's automatically put it into the graph entry line. And all I have to do now is press enter. We notice that the graph is not quite on the screen, so we can go around and have a look at our values. The main one of interest here, we don't see the bottom of the graph, so we'll just double click on that, and I'm going to just guess a value, let's say about -40, so that the graph will fit in there. And we see the graph. If we wanted to, we could tidy up these other ones, but there's no need because we're looking at the point where x equals 6. Okay, so let's have a look what our menu brings up on the graphs page. So if we go to Analyze Graph, and it says number 6 to y dx, and we see there's some values as we go around, and we could drag this around and hopefully get 6 if we could, but it looks a little bit difficult. So if we just type in 6 and press enter, it gives us 9. So at that point, the tangent line here would have a gradient of 9. So if we started graphing first, we might decide to work out the value there. So now we want to find the coordinates of the point on the function g of x equals 3 square root of x minus 2 minus 6, where the derivative is 2. Okay, first thing we're going to do is define our function. So I'm going to use the assign key this time. So g of x, the assign key. It's a different way of doing define is control and just above the template there. And we'll put in our rule 3. And -6. Press enter. Now, take the derivative. So we'll use our template shift minus x. Again, I'm going to press the var key, but I have to do that when I'm inside the bracket. So press the var key, and we'll select G. I could have just typed it in, but we've got G of x, and we're going to press enter. Okay, there's our derivative. Now we have to find where the derivative is equal to 2. So menu 3. I like to press the buttons on the calculator because if I use my finger on the touchpad, they seem to just click onto the next item in the menu list. So pressing the buttons is much better. So we're going to solve, and I'm going to hit up arrow in the history and press enter because this is our derivative. I need to let that equal to 2. I've got to solve for the variable x in there, and then press enter. So we now know what the x value is, where the function has, or the tangent line to the function has a gradient of 2. We're asked to find the point, so we need the y value as well. So if we press var and the g of x, if I use my history and go up arrow, I can just paste that whole part in there. I can go and delete. I don't have to delete the x equals, but it makes it look a little bit neater. So we now have the coordinates of this point being 41 on 16 and negative 15 on 4. Okay. Now we're having a look at the gradient function, and we know that it has to deal with a lot to do with tangents. So we've just set up this graph. This looks like a cubic graph, and I'm just going to grab this point and we'll see what happens. And over on the left, on the right-hand screen, I should say, we're on the left hand. On the right-hand screen, we've got the y dx, which should come out, and then we'll just see what the shape of the graph looks like. So I'm just going to grab that point. I'm just going to move it. So as we see the tangent line moves, we see the shape of the graph appearing on the right-hand side. I'm just going to go down and drag it down towards the bottom there, going to the negative. And we see, as we know, so I'm just reinforcing what you've learnt before. And we've got what looks like a quadratic. And there's our derivative graph, which lines up on those tracing points. So we can see some things that we've learnt before on that, just reinforcing things. And that's just a picture of all the coordinates that the trace picked up. Now again, we've got a cubic again, but this time we've got two stationary points that are there, and we just want to see what happens with the trace as we go through. So just watch the green lines as I move it back that way. So as we're about at the stationary point, we see that when we're actually on it there, that the derivative is 0 on the right-hand graph, the green dot. And then as we go down, we have a slope which is positive, and it's increasing as we go down, and we see that occurring there. Okay, and we're just going to go back the other way. And in here we have a negative gradient past that stationary point, and we're going down negative gradient, and we know that it increases, and it increases to a maximum somewhere about there, which is the point of inflection on the graph, and then it comes back up and approaches 0 at that stationary point there and continues up. So that's just the view how we have the vision of the gradient function or the tangent line that is there. Okay. Now we want to find the equation of the tangent line to the function h of x equals x cubed minus 5x when x equals 2. And we've got a form we're going to give it in, y equals mx plus c. Now, if this was a technology-free question, we'd be solving this equation, y minus y1 equals mx minus x1, and we'd put in the gradient, the derivative there, and substitute in point. So we could do that if we really wanted to, but we're not going to do that. We should know by now that there is a inbuilt function that TI has to do this. So as always, we're going to have to define our function, h of x. We'll use the sign key again. So control and template. And we've got our x cubed. And minus 5x. And enter. So the next thing we're going to do is I'm going to put a y equals here. We don't need to, but I'm going to put a y equals there. And we're going to go menu. And we're talking about calculus today, so probably the calculus menu is a good idea. And if we look at number 9, it says tangent line. So tangent line comes up, and we have to put in the function, which is h of x, and I'm going to type it this time. And then we're going to go at the point that it occurs at, and I can just put x equals 2. If I press enter, we have our tangent line, y equals 7x minus 16. So hopefully you all know about that tangent line equation. Okay. Now, what we might like to do is just have a look how we could do this on a graphs page, because we might have the graph up. So this time, I'm pressing Control G, you notice that I haven't defined the function, but we know it was hx, so I could just go in there and say h of x and type that in. And there's our function. And it fits reasonably well on the screen there, so we'll leave it at that. The next thing I could do is, quite often the geometry menu is not used very much. So what I'm going to go and do is put a point on the graph. And we want a number 2 point on. I'm just going to click a point there. There it is. And that's good. Okay. And I'm going to turn the tool off by pressing Escape. Pretty close to the -2, which is what we're talking about. So that's pretty good. So all I have to do is double click on that and delete off the decimal part and put in there. We see that our point is -2, so if we were doing it by hand, we would have had to work out the y value there. Now next we're going to go back to the geometry page again, and the tools there, and this time we'll go points and lines, number 1. But if we see number 8 has this tangent tool, and so I'm going to press that, number 8, and then up here, if you're not quite sure what to do, you can just read the instructions which are up there. And I'm just going to come down and I'm going to click that and turn off the tool. And there we have our equation of the tangent line at x equals -2. So that's another way that you could do that. So if you'd drawn the graph first, and you could have done it that way quite easily. Okay, just another view about some derivative graphs here that we're looking at. Now, down here we've got the red graph, we've got a dot that we can move here, a point, and up the top here we can just see the derivative graph just sneaking into the picture there. And the blue graph is our cubic that's here. And we're just going to go through and just see what happens. Just another view of seeing what's going on. So we're at the 0 there. As we come up, we see that that line is approaching with the black line is approaching the x-axis. As we get closer to there, it had the maximum there. So we could try and get that back there. There it is, touching on the axis there. Might be an easier view to see. And as it comes down, we see that the maximum is coming up now. The minimum of that black parabola is coming up there somewhere around here. And that's the point of inflection on the cubic graph. And then it's coming back up and turning. And we notice that from our factorized equation of x minus 2 all squared, we should have realized that there was a stationary point there. And our quadratic should pass through that, which it does. And then it continues on as we go up. Okay. And there we see our derivative graph that's there. All good. Now, find the coordinates of the stationary points of this equation, fx equals x minus 2 all squared times x plus 3. Now, we've seen here, if we look at this, this is the repeated factor that I mentioned before. So we assume that one of the answers will be at x minus 2 or x equals 2, and we let that equal 0. So we really need to find the other one. And so we've got to define our function. It's there. Okay, so now we'll just do our signed again. Control and signed. And this time, because I've got this up here, I'm just going to go up here and do a copy and paste. It's like the history, but that's a notes page up there to do my text. And if I go Control C, remember all the Microsoft commands work in the TI calculator. So I'm going to paste that. I'm going to press enter. Now, one way we could do this, as we sort of did before, we could take the derivative, let that equal 0, find the values, and then substitute them back into the fx equation to work out the coordinates. But this time what I'm going to do is I'm going to use a different command. So we're going to go Menu, 3, and we're going to use 4 zeros. And what I'm going to do, I'm going to take the derivative and then work that out and see what happens. So again, we're going to go shift and minus. We've got our x. I'm going to go into the bracket there. I'm going to press the var key to see what's defined. And then we're going to put an x in there. And anything else we have to do, we've got to put in the syntax. So if you're not quite sure of the syntax, you can always go to the catalogue or the book to see what's going on. Now, zeros. So the interesting thing about zeros is that it gives us both answers for where the graph is 0 crossing the x-axis in this braces form, which makes it nice and neat. It doesn't say x equals, if we did solve the equation, it would say x equals minus 4 on 3 or x equals 2. And then it's a little bit messy to try and work out the y values. But to work out the y values, we just hit var and select our f function. And if we go up in the history, we can just plonk that in, I guess you could say, and then press enter, and we get our two values. So we have the most negative station point would be at minus 4 on 3 and 500 over 27. And as we knew already from the equation, the other one would be 2, 0. Okay, the next question. If f is a restricted domain function from -2 to 3, and it's mapped onto real numbers where f of x equals x cubed minus x squared minus 8x plus 7, we've got to state the domain of the function. Okay, so let's just have a look at that. So we've got to define our function again. So f bracket x is assigned to, and our x cubed minus x squared minus 8x and plus 12. Okay, and it's restricted, so we're going to put in our control equals and back arrow template, and we've got our minus 2 is control template less than x, which is control template, the equals button, less than or equal to, and we've got our 3 and press enter. Now, we all know that there's some sort of domain function, don't we? So, got to go to the book for that, and I've already got on it because I've used it before. Remember that if you press the letter E, it goes to the start of the E's. We press the letter G, it goes to the start of the G's, and then you scroll up or down to the thing. So it says we've got to put the expression and the variable in there. So we're going to press that and put it in, and the expression is our f of x, and let's type that in, and the variable was x. So let's see what happens. Oops. Oh, I missed a comma in my haste there. So let's go back, put a comma. And now, look at that, isn't that beautiful? So, but that's the domain of the original function. So let's go up. So it agrees with us. Let's go up and try that again. So this time we're going to just delete this part off because you can edit it so we don't have to type things in again. But we want to go shift and minus. And then we're going to go x and then bracket x. Okay. And we press enter and oh no, it doesn't give us the answer. So we're sort of stumped there, aren't we? So this time what I'm going to do is I'm just going to go shift and we all start wondering what's going on. And I'm going to do this time. And I'm just going to put in the function of f bracket x. Okay. And straight away when we do the derivative, it actually lists off the domain for us there. Okay. One thing to note about that, when we compare it back to our original function, up here. We'll just scroll up a little bit more. The 3 is not included when we do the derivative. It's there. Okay. So, and we're supposed to sketch the graph of the derivative showing all relevant points to correct to 2 decimal places. Okay. So let's go across and Control G. And I'm going to go up arrow and press enter because I already defined it there. And there's our graph. Just have to change this here. Double click on that. And let's go up to, I don't know, 20. We'll try that. So that looks pretty good. There's our graph. We'll shift this out of the way. Okay. And we could probably just make this a little bit better there. Let's go to 5 and press enter. And we're going to change this one to 5 as well. And we'll make it -5 and press enter. And it's all good. And so I'm just going to push that across there. Now we've got to sketch our graph of the derivative. So I'm going to go Control G. Now I've already entered this in. So you can go in and put the derivative template in. You don't have to find the actual derivative and then put it in, but that will work. So I'm just going to press enter, make that work. There it is. Now we notice that I'm just missing a little bit there. So, and we might have just a little bit of interesting time to get to this value. So this way is to come over to this one. If we have that trouble, I just got to deselect that graph and double click on that. But if I hit tab, it goes down there, and we're just going to go say to -10 in there. And there's our graph. And we had to sketch the graph. So a couple of things we've got to find. We could click on this and change the scale there. If I change that to, say, 1, and we could see this will be going through at 2, 0. We've got to work out this value there, and we've got to work out the point here. We already know what the endpoints are, so that would be good. And let's, the x values are the endpoints, so menu, and let's go Analyze Graph, and let's pick the 0 first, and the graph. And just drag, oops, don't want to get that. Okay, let's go there, drag that across, and then menu, Analyze Graph, and 0, and there's our graph, and drag, we know that's 2, don't we? So it's just verified that that's 2, and we really need to find this value here, the turning point. So menu, Analyze Graph, and our minimum 2, and we're just going to pick the graph, and left bound, right bound, there's our minimum that's there. And what else do we have to find? Let's just go back and have a quick look at the question, and it said 2 decimal places, so that's all good. Just verify with that. This one's at 3, so if I just hover over, this is the turning point, if I hit the minus key, it will actually decrease a decimal place that's there. So that looks good. And anything else that we need to find? Maybe we just hit a trace there and see what happens. Now, if we graph trace, let's just swap to the other graph by hitting down arrow. And if we go to -2, I'm just going to type in -2 and see what happens. And it says that it doesn't work, but it says -2 is undefined. So it's just got to be aware about working out the endpoints. So what the best way to do that would be substitute -2 into our equation of F1 on the other screen and 3 into the equation to work out the Y values, and then that question's all done. Okay, now just to check about this, now these points here I've actually put in separately. I haven't done them. The graph, the calculator won't put these dots in. I've done that manually. But just to see between the function, just to check to see whether the function f of x, the blue graph, it's actually defined here at 6, and we've got this table of values. So I know that's 6, so I could work that out like that. I've got my 2 values that I've worked out here. But if we press across this arrow at the bottom, I can see the same values here, where it says now at 3 it's undefined. And if I scrolled up, I'd also see that in the table of values, it would be undefined. So you can have a look at that when you get the file. So now this was just another dragging very quickly about an exponential graph. Y equals e to the x plus 4 is the red graph. The derivative is e to the x. And it's just showing you that the graphs are identical except for a vertical translation as they go up. So it's just showing you why the derivative of e to the x is e to the x. And we've just done a translation so we could see that that was the case. Now I'm aware of the time and just a couple of glitches beforehand, and it's just taken a little bit of time there, but we'll have a look at this question and then I might just show you. So if f is defined over the real number system, the domain is R, and we've got this exponential function. And we need to find the value of the given. So we've just had the value, something's just disappeared there out of the text there. Find the value given that the function passes through the origin. So I'm just going to flick, I see the time, so I'm just going to flick through to some of our answers over here, and you'll have access to all of these if you've listened to this live and demonstrations that are there, so you can see that these are all the questions. I'm just going to go through like a working sort of thing for the last question since I can see the time that's there. Okay, so that's not our question yet, we've done that one. And it's that. Okay. And here we are. So what we had to do is find the value of A, which has disappeared there, and given that the function passes through the origin. So straight up, we would just say, solve the function. Now, if you notice, this is actually a notes page. And when we come in to put in what's called a math box of our equations, all I've done is type them in. So to get a math box, I've just gone Control M. Oops. No, Control M. Okay, and then we type our formulas inside there, just as if we did. And when we have math boxes, when we press menu, the calculations that we know from the calculator page are just down at number 6, and they're all the same as number 6. But I'll just walk you through these since we're a bit short of time and we're actually a little bit over. So all I do is solve this function at 0 and I get my A as 3. The next part of the question was that find the point on the function where the tangent line has a gradient of -2. So once we worked out A equals 3, I substituted in with the given symbol. This is all in math boxes, okay? And then it gives me an equation. Now this time what I've done is I've defined the derivative and calling it d of f and assigned it to that value up here. And then I've worked out when the derivative is 0, that's 1. And then we've come through here and we said I've got to find where the derivative, now that doesn't need to be there, that one. So, and we had to find when the derivative is -2. So just as before on the calculator page, we typed in the solve features. We're just doing it in a math box. And we can go and update that at any time that we want by just clicking in the box. But we know that the x value is -log2, and therefore when we substitute -log2 in the formula, and again in another math box, we get that at -3. Okay, I am aware of the time, and I just wanted to show you an interesting thing with the CAS graph. Will be a couple of minutes, and I'll just race through it. Again, if we've got our red graph, which is cos x, and we've got the derivative sin x, we can just see where all the stationary points meet up with the inflection points going through. And when you get a copy of this, you can play that and just see how they line up as they go through. Okay, and there's just one last question which was on the sheet, which doesn't take too long to do if you set it up this way. And now we've got to find the product of the x values of all the stationary points of y equals 2 sine bracket 3x plus pi and 2 plus 1 in between this domain. Now the first thing, of course, you're going to do with all these things is you're going to define your function. Again, I've done it on a notes page just to show you how the notes page works compared to a calculator page. And the first thing I do, I could use solve. And as we mentioned before, when we use solve, we get all this x equals pi and 3 or x equals 2 pi and 3. or x equals 4. Now, could you imagine now multiplying all those and typing them all, copying and pasting? Well, that's a little bit awkward. So instead of using solve, we use zeros, as we did before. So zeros puts it in the braces, and it's all there, beautiful to do. Now, the product. In the catalogue, there's actually a product function that we can use. And again, it's in a math box. So I've gone to the catalogue and produced up that product function, or if you remember it, you can just type in product with the brackets. And then I just copied these values in and then pressed enter. And the answer to that question, the product of the x values of the station points, is 8 pi to the power 4 on 27. So I just apologise for going a little bit over time there. So I hope you've got something out of this webinar that we've done. And I've just seen a little note in the chat there. Yes, there's also a sum feature. So if you did go to the revision webinars that we had in the term 1 holidays, I actually used one which had the sum feature. So look on the student blog to get access to those videos and all other videos that TI has. So thank you.